Welcome back to another presentation on time domain specifications of control system. We are looking about, which is one of the very important chapter in this control system subject. And if you recall our previous presentation, there we have seen some examples on these time domain specifications. And if you recall the previous presentation also, there we have seen the steady state error. What is the steady state error and what is the expression for steady state error? And for different inputs, means for unit step input, what is the steady state error? Similarly, for unit ramp input, what is the steady state error? And what is the for unit parabolic input, what is the steady state error? These expressions we have seen in last, I think, if you see the presentation, uh, I mean lecture number 37. So today we will see about little bit more about the type number. I think this also I have covered in previous presentation, but in today's presentation I would like to give little bit more explanation about the type number, what is a type number, and the steady state errors for a different input and with different type numbers of system. Clear? So just we recall our previous presentations. We have seen that the steady state error is denoted by E suffix SS. This is the steady state error. This already we have seen a mathematical expression for ESS is equal to limit s tends to 0 s into E of s. Clear? And further, this can be written as limit s tends to 0 s into what is E of s? It is R of s by E of s is nothing but your R of s by 1 plus G of s into H of s. This is the expression for your E of s. You must remember always this. Clear? Therefore, this is the steady state error expression. ESS is equal to, steady state error is equal to limit s tends to 0 s into R of s by 1 plus G of s into H of s. From this expression, we can say that, or you can observe that the steady state error E of SS depends on input. R of s is your input. Similarly, G of s, this is the forward gain or the forward transfer function, sometimes it is called as G of s, or simply gain of the amplifier. Therefore, your E of SS steady state error will depends on input R of s and in your G of s. Therefore, that's why we have seen in previous presentation R of s means input. So we have applied different types of inputs. We have taken into consideration with different inputs. What are those? The first one is unit step input we have seen. Second, unit ramp input we have seen. And third, unit parabolic input we have seen. So for unit step, what is the steady state error? For unit ramp, what is the steady state error? For unit parabolic input, what is the value of steady state error? We have seen this in the last presentation. Now in today, what we have seen is that, so what is the steady state error? For different type numbers actually. So we have seen what is a type number, what is type 0 system, what is type 1 system, and what is type 3 system, and so on and so forth. For different types of, for the different type numbers of system, or for different type of systems, for giving different inputs, what is the corresponding values of steady state errors for those systems? That's what I am going to explain you in this presentation. It is very important. Definitely you will expect questions on this in either GATE as well as UPSC's IAS examination. Therefore, let us listen carefully, and it is very interesting and it is very important also. So remember that the steady state error formula, limit s tends to 0, s into r of s by 1 plus g of s into h of s. This is the standard formula for steady state error. Now so we have seen that. Let us consider the steady state error for with input r of a unit step input. So consider for unit step system, or consider for unit step input, that is your unit step is nothing but your r of t is equal to u of t is equal to 1. This we have seen, where for t is greater than or equal to 0 and it is 0 for t is less than 0. This definition is already I have given in last presentation. You please refer that. So if the r of t or u of t is equal to 1 for this unit step, this is what the unit step function definition. So for the unit step input, what is the steady state error we have seen? What is the steady state error? So your steady state error is nothing but what we have seen. It is 1 by 1 plus limit h tends to 0, it is g of s into h of s. This is what we have seen. So because as I have explained you very clearly in the last presentation, that's why in this presentation I little bit go forward, because okay. So this is the steady state error for unit step input, that is 1 by 1 plus limit s tends to 0, g of s into h of s. Clear? And further, how we can write this? 1 by 1 plus kp, I am writing this as kp. Remember that ESS is equal to 1 by 1 plus kp, where kp is nothing but this much. Clear? kp, where this kp is equal to this much, limit s tends to 0, this is g of s into h of s. This is what your kp. What is kp? Sorry, it is positional error constant. kp is nothing but positional error constant. Positional error constant. Limit s tends to 0, g of s into h of s. That is the value of s. Now, now for different for type 0 system, similarly for type 1 system, for type 2 system, what is the steady state error value? Okay, what is the steady state error value when the input is unit step? Like that. Now let us consider the type 0 system. For type 0 system, for type 0 system, what is the type 0 system? What is the type number of a system? This I already explained you also in the last presentation. The type number is nothing but the transfer function is something like this. So here, just to recall that your positional error constant kp is equal to what we are writing, It is limit s tends to 0, clear, g of s into h of s. This is what your limit s tends to 0, g of s into h of s for kp, and further limit s tends to 0. So for type 0 system, your g of s into h of s something in this form. Okay, for type 0 system, your g of s into h of s is something in this fashion. What is that? It is some k into constant k into some, it is called some s plus z1, s plus z2, and s plus z3, and so on and so forth. Means some numerator by some denominator, means s plus p1, s plus p2, and s plus p3, and so on and so forth. This is the form. Actually, this is in this form. It will be in this form. So, okay, some constant into numerator polynomial, denominator polynomial. This is s plus z. What is z1, z2, z3? These are the zeros of the transfer function, and p1, p2, p3 are called as the poles of the transfer function. And furtherly, you can write for our convenient that limit s tends to 0, and this k will be there. So means that from numerator you will get zeros only. That means, so you can write z1 into z2 into z3, and so on and so forth. You will have zeros only in numerator, whereas in denominator you write p1 into p2 and p3, and so on and so forth, and so on and so forth will come. Then means that what? Actually, zeros nothing but the values, basically some value. These are the constant values. Say for example s plus z1, say s plus 1, s plus 2, s plus 3. Let us say if it is s plus 1, then s equal to minus 1. Minus 1 is a constant. Like that, s plus 2, s equal to minus 2. Or say for s minus 3, let us say it is s minus 3, then s equal to 3. Therefore, z1, z2 are the values, constant values. So from this you will get constants, poles also constant. So constant by constant, again it is a constant. Therefore there is no, if you apply s tends to 0 to this everything is a constant. If you apply the limitation to the constant, your answer is constant. Therefore you will have constant here. So what I mean to say is that the positional error constant is a constant you will get for type 0 system. For type 0 system, the positional error constant, this is called positional error constant. No, this position error constant becomes constant. Then if you apply this kp value in the steady state error, you apply this kp value in steady state error for this unit step, then what is the steady state error? Limit s tends to 0, s into, total is not required, directly you write not required to complete the definition. What is the steady state error for this unit step is 1 by 1 plus kp. This is final expression, no, for ESS, for unit step function. Then what is the kp value? Kp is a constant, then you write here constant. Therefore it is 1 by 1 plus kp value is some constant. We don't know that value, but it is a constant. So constant plus 1, it is a constant. So means the denominator total is a constant. Again it is 1. 1 is a constant again. Constant by constant, constant. Therefore you will have constant. Therefore ESS is constant. Therefore from this you can say that, you can tell that, what you can tell? So for unit step input, with the unit step input for type 0 system, that steady state error is a constant value. Or otherwise you can say that for type 0 system, the steady state error is a constant. Steady state error will be available for unit step input or with unit step input. Clear? Therefore for type 0 system, with the input of step input, you will have a constant steady state error. That is what otherwise. Okay, for type 0 system, with the step input, we will have constant steady state error. See, this is what? Clear? Understood? And now let us see for same expressions with type 1 system. Say for example, it is for type 0 system. We have seen what is the positional error constant. This constant we have substituted in the definition of the steady state error. Then we have obtained the value of steady state error. That's all. That's all. Therefore, likewise they will ask you in examination for type 0 system with the step input, what is the steady state error? You have to write that. So that is a constant or infinite or 0, like that they will give you the options. Then you must remember this. For type 0, what is the input? You must remember what is the input they are giving, what is the type of this one, and basic definition of corresponding steady state error definition. This is the basic definition. ESS is equal to 1 by 1 plus Kp is the steady state error definition with unit step input, for unit step input. Clear? So this is one important thing. And similarly, write type 1 system. So now you see type 1 system with the same input. I consider the same step input, and just I am changing to system. Now I am considering type 1 system. So everything is same. Everything, the definition, everything is same. Type 1 is something in type 1 system, your G of s, H of s, how it changes, that's only you must remember. So for type 1 system, what is the form of G of s into H of s? Very simple. This everything is same. Type 1 is nothing but in the denominator part you will have s, that's all. Because remember that, recall from our previous presentation, the type number is nothing but in the denominator polynomial s power n into s plus p1, s plus p2, s plus p3 must be have. Denominator is however it is there, because s plus z1, s plus z2, like that. In numerator polynomial you will have zeros only, whereas the denominator is very very important. In denominator polynomial you must have s power n. S means s into s plus 1, s plus 2, s plus 3 form it should contain. Then that s, okay, nothing but s power n. So that n decides the type number. Therefore here type 1, let us consider, say for example, if s power n is there, because you are considering type 1, then definitely this g of s into h of s must be in the form of the same, except that you must have in the denominator s power n. You must have it, because as you are studying type number. Previously type 0, therefore type 0 nothing but s power, you don't have anything there, no s term there, that's why it is a 0, because s power 0, no, s power n, if you substitute n value with 0, s power 0 is 1, s power 0 is 1. Clear? That is why it is a type 0 system, whereas type 1 is nothing but you must have s, where n value is 1, so n value is 1, s power n is there, that if you take n value is 1 here, then s power 1, that n value is 1 gives type 1 system. So in type 1 system you have one s, remember like that. Type 1 means one s you must have. Now clear? Now the same, only thing is the denominator, no, you will have s only, that's all. So s into, you add everything is same. So in denominator you just add one s in denominator, then remaining everything is same. Limit s tends to 0, k into s plus z1, s plus z2, s plus z3, everything is same. Here also same, here also everything is same, only s will come. Now what you will write? Limit the apply the limitation s equal to 0 value here. You apply s value here. So this everything is constant. It is 1 by s basically. If you apply s equal to 0 here, this everything 0, no? 0 is something, what is this actually? 1 by 0 form. Is it not? 1 by 0 form. Let us call some constant. It is, obviously you can write 1 by 0. You are applying 0 no here. You apply 0 here. It is 1 by 0 basically, some constant by 0. It everything becomes 0. So 1 by 0 is, what is that? Infinite. Infinite. Therefore what is the position error constant? Position error constant what? infinite because of 1s. If you apply limit s tends to 0, means that in s place you apply 0, 0 into something will become 0, something by 0 is infinite. That is what position error can. Therefore, for type 1 system with the input step input, your position error constant now became as infinite. Then substitute this kp or positional constant equal to infinite, this value substitute in this definition. Then what is steady state error? What is the steady state error for this input? So instead of constant, instead of earlier it is constant, now it is infinite. It is infinite now for type 1 system. 1 by 1 plus infinite. So further you can write here infinite plus 1, infinite. So 1 by infinite equal to 0. Therefore, here in this case, your steady state error equal to 0. Okay? Initial. Understood? Therefore, for type 1 system, with the input step input, for type 1 system, you have 0 steady state error. You have 0. The steady state error becomes 0. Understood? And similarly, now come to the type 2 system, what we'll see. Say for example, type 2 system. Type 2 system. So I think you already guessed it, what it could be. Very easy, no? So type 2. So now tell me, for type 2 system, what you will do? In the denominator part, you have, instead of s square you should have. Means here everything is same, you should have s square here. Means 2 s square term. Then everything is same, only thing s square will come here. Again same story, same. So if you apply limitations here, yes, again it is 0. 0 into every same, infinite, again steady state error is 0. And even though if you write the type 3, again same 3, same answer will come. Therefore, here we can conclude for this step, for the step input. So for the step input, for type 0 system, only the steady state error is constant, and from type 1 onwards, type 1, type 2, type 3, and if you go on, okay, then your steady state error becomes 0. It has constant steady state errors from type 1 onwards. For type 1 onwards, okay, for type 1 onwards, you will have the steady state error 0 for the step input. So for the step input, we have seen type 0 system. What is the ESS value for type 0? What is the ESS value for type 1? What is the ESS value for type 2? Like that. Clear? So now we change the input. Clear? Now instead of unit step is over. Now come to the unit ramp input. Same in the unit ramp. So I will write here unit ramp. For unit ramp input, what is the steady state error and what is the how it will becomes. So here unit ramp is nothing but, you know that unit ramp means your R of t is simply, tell me what is unit ramp. Unit ramp is nothing but R of t equal to t for t is greater than or equal to 0, and it is 0 for t is less than 0. It is a ramp signal actually. Okay. R of t is equal to t for t is greater than or equal to 0, and it is 0 for t is less than 0. That is the input, means ramp input. That is the definition of ramp input. Clear? So now here for the ramp input, the steady state error value is, what is steady state error value? 1 by kV, 1 by